The first welding machine that we're going to introduce is the shielded metal arc welding machine. A lot of people refer to this as a stick welding machine. It's one of the earliest and simplest types of electric arc welding machine. It has relatively few controls and relies on the operator to really get the best weld out of the machine. There's one connection here for the electrode. There's one connection for the ground clamp. That's what completes the electric arc. There's a dial here to set the amount of welding current, and then a selector up here at the top right that allows the operator to select between alternating current, direct current straight polarity, and direct current reverse polarity. We'll talk a little bit more about polarity when we get to the actual welding process. Now, these machines are very, very simple. In fact, they really don't have any moving parts at all. The only moving part that this machine has is a fan to keep it cool. So when we look inside, we can see that really this machine is one big transformer. It takes electricity that's provided to us by the grid, which is 480 volts and about 20 to 30 amps. And then it steps that down to a relatively low voltage and a relatively high amperage. It does all that with, as I said, no moving components. So it's a very reliable, very robust form of welding, and that's why it's been prevalent for so long. Here on the front, you can see connections on the right for the electrode, and on the right for the workpiece, on the left for the workpiece. So on the left, we have this connection, which is our ground clamp, the big copper, very conductive clamp to help complete the circuit. And on the other side is the electrode stinger. And this is an electrode holder. This is our stick electrode. That's why they refer to this as stick welding. So it mounts in here. And then when I give the demonstration on actually striking an arc, these pieces will come into play. The second type of welding machine that we're going to talk about in this class is the gas metal arc welding machine. Now it's a little bit more complicated, has a few more parts than the shielded metal machine, but really functions on the same principle, which is on electric arc to generate the molten weld pool and a consumable electrode to actually feed filler metal in. So some of the similarities you'll find on this machine that you'll see on the shielded metal machine is that we have a ground clamp that we use. We connect to the workpiece to complete the electric arc. There are controls here on the front, only now we're changing the voltage instead of the amperage. And we'll talk a little bit more about that when we get to the actual welding demonstration. And then there's also our electrode holder here on the side. The electrode holder looks a little bit different because it's no longer a stinger that holds an electrode of limited length. Now, instead, this is a hollow core cable, and running through it is our consumable electrode in the form of wire. So there's an additional control here on the front for wire speed, the rate at which that wire comes out. When you look at this wire, which is our consumable electrode, you can see it here. It's mounted on a spool, and if you can see it, it actually bears a copper color. It is still steel wire, it's mild steel. However, we give it a copper coating to protect it from corrosion. This process is particularly intolerant of dirt, impurities, and rust. So we have to protect everything, including the filler metal, from corrosion. And we do that with that really thin copper plating. In addition to the electrode being fed through this cable, we're also going to feed a high pressure gas. This is a shielding gas, and shielding gases are typically inert or semi-inert gases. So those are the gases from the right-hand column on the periodic table. And we sometimes combine the inert gases with some more economical gases like carbon dioxide. But the goal of these gases is to push the atmosphere away from the weld pool and encapsulate it so that we don't get the harmful effects of oxides and nitrides that come from the welding process. So when I pull the trigger on this welding gun, that will start not just the flow of this welding gas through the nozzle here, but also will start these rollers pulling the electrode through. Because we can have spools of wire that go up to hundreds of pounds, this process suits itself much better to high volume manufacturing, things like robotic welding, because we don't have to continually replace the electrode like we do in the shielded metal arc welding process. Other than that, it's still a very similar process to the shielded metal arc welding in that we have to establish a weld pool, we create a coalescence of metal, and then we add filler material to reinforce the joint with added cross section. Before we can begin the process of discussing machine settings and material preparation, we have to talk about safety. Now, there's a lot of hazards in a welding shop, and they may not all be as obvious to you as you would think. Certainly, there's going to be lots of heat. The heat that we use to melt the metal to join them is going to stay in the material for quite a long time, especially when the work pieces are very thick. So sensing metal for radiant heat with the back of your hand is always a good measure when you're in a weld shop. In addition to that, you have to protect yourself and protect the equipment you're wearing from things like sparks and most importantly, light. A lot of people don't think about the level of visible and ultraviolet radiation that comes off of a welding arc, but if you want a good idea of how damaging that is, go into a weld shop that's been around for decades and take a look at the paint on the wall. You'll find that the paint that's nearest the welding booths will be faded quite aggressively, in fact. So the amount of light energy that's coming off of these processes can be really hazardous. So the first and most important piece of equipment we have is our welding helmet. And this has a tinted visor that is going to block a lot of that damaging light from coming through and is going to allow you to get in really close and see the weld pool quite clearly, because that is really critical to making a good weld. So these shields should cover your whole face, and then these visors are graded in different tints called shade numbers, and you have to make sure that the shade number is appropriately aggressive for the type of welding you're doing. Things like oxy-fuel welding don't generate nearly the level of damaging light that arc welding does, and so there's a specific shade just for that. In addition to that, the mask is going to protect your face and neck from things like sparks and slag. Another important piece of protective gear is some rawhide gloves. You'll see these are full gauntlet length gloves, and again, there's a lot of slag and sparks coming off the workpiece, and we want to protect your hands while you're welding. And similarly, we have some heavy cotton clothing here. This is a cotton welding jacket, and it's flame retardant. You can also get these rawhide jackets like the ones that I'm wearing. They're a little bit more expensive, but they also protect your upper body and arms, and to some extent your neck, from the sparks and the light as well from welding. In fact, if you don't wear one of these, even if you manage to avoid the sparks and the slag, you may still find that you've got a pretty aggressive suntan at the end of the day. That's because the light radiation coming off of these processes is very comparable with what comes off of the sun. So protecting ourselves not just from heat, but also from light is very important. There's a couple of tools you're going to see me using. A pair of pliers is important because whenever we want to move our work pieces around, we don't want to take the risk of burning or melting the gloves that we have. You can see there's some damage to these already from people that didn't take that precaution. So the pliers are always what we're going to use to carry around work pieces. Again, the amount of residual heat that you'll see in these work pieces is more than enough to burn you. So in a weld shop, we always use something like a pair of pliers or tongs to carry around the work. When you see my demonstration on the shielded metal arc welding process, you're going to see me remove slag, which is the solidified flux layer that occurs on top of the weld, using a chipping hammer, which is specifically this part of this tool. There's also a wire brush on it. And one of the important precautions to take while using this tool is that we're going to be wearing safety glasses. So even when you don't have your welding mask on in a weld shop, it's still very important that you're wearing some safety glasses, because when I chip off that layer of solidified flux, that slag, you're going to see almost a glass-like material flying off in all directions. So all of these safety tools are important, and you're going to want to wear these every time you're in a weld shop. And you're also going to want to take care to make sure that the people around you are wearing safety equipment. You would never want to strike an arc, for instance, near someone that's not wearing the appropriate safety gear. Even momentary exposure to the light can cause permanent damage. And then similarly, leaving things like hot pieces of metal and live electrodes around are not safe practices that you would follow in a welding shop. The purpose of this exercise is to give you some experience with the different variables that take place in the welding process. Typically, I split the groups up and assign them either a shielded metal arc welder or a gas metal arc welder. I give the groups a stack of these coupons, and then the groups set to work welding these together and testing their welds. Along the way, they learn about things like electrode, angle, welding gap, amperage, voltage, and so on. In an attempt to give that same experience in a video, I'm going to go through and I'm going to weld each of these samples with the same electrode on different amperages, so that you can see that we can get welds that look passable, that appear to be good welds, but in fact aren't. So we'll weld these under different conditions, then test them. One of the great advantages of the shielded metal process is all these different flux coatings that we can put on the electrodes. So these three electrodes here, for instance, all have the same base metal. They're all mild steel, but they have different flux coatings to give them different behaviors. So one of the things I want to do to show that off is to run a few test beads here on a sample piece, so that you can see how much effect that flux has on the finished weld. So I'm going to start by welding these samples. I'm going to turn on my machine. I'm going to set the amperage at 50 amps, and then I'm going to strike the arc and weld across each sample, increasing the amperage as I go. So you'll see me start here at 50 amps. And then once I weld each sample, then we'll look at them, and then we'll break them, and we'll see how much the weld actually penetrated down into the work. A good weld has 100% weld penetration. So I have my electrode here. Turn the output on the machine off. 50 amps is our start. I'll weld sample A. You'll see me hold the work pieces down. I'll tap the sample a few times. You'll see some sparks. Ultimately, you'll see the arc occur and create the weld pool. I'll move across and finish the weld. Okay, I'll increase the amperage and go on to the next sample. 60 amps, we'll weld sample B. third sample will be at 70 amps. And then I've consumed enough of our electrode that I'll have to change it out before we go on to our final sample at 80 amps. Okay. Now I'm going to quench each weld. We'll take a look at it and then we'll break these welds. Our first weld has a relatively narrow and tall bead. It didn't have enough amperage to really burn into the workpiece. When we look at the opposite side, we can see that there's some discoloration, but really there's no weld that penetrated all the way through the workpiece. Our second sample has a much wider bead now. There's enough amperage that the weld pool is starting to really melt into the material. In addition, you can see in the second sample that where we started, the weld bead is relatively narrow and high. Where we finished, it was relatively wide and shallow. That's because as we welded, we heated up the workpieces. That allowed the metal to diffuse more into the base metals. You can see here that there's just a few points where the metal started to peek through. We didn't have full weld penetration, but we're certainly getting there. The third sample has a much wider bead and it starts to flatten out much sooner. We're imparting a lot more heat into the workpiece. Now it looks like the two workpieces may have been mismatched a little bit, but I can see metal is creeping through all the way along here. So we can see just barely metal starting to penetrate through the entire length of the weld. Our third sample has excellent penetration. It's burned in all the way through. We have complete metal on both sides. I can see that the metal is burned into the base metals completely. It got a little hot here towards the end. We had heated up the whole workpiece and I held the electrode there just a little bit too long, and at the finish some metal actually melted off. But I suspect that this weld will be the strongest. In order to give you some perspective on how much influence the flux has on the weld itself, I'm going to run a couple of beads with 4 different electrodes. I have here 4 electrodes with fairly different flux coatings. The metal themselves is very, very similar between the 4. 2 of them have 60,000 psi filler metals, the other 70,000, but the truth is they're both relatively close to mild steel. The major difference between these is the flux coating. So as I run these 4 beads, I want you to listen to the difference, and then we'll look at the difference between the 4 beads. The 4 different electrodes that I'm going to use are 6011, 6013, 7018, and 7014. Even though the purpose of this lab is to compare some of the shielded metal arc welding variables, I still want to give you a demonstration on the gas metal process. Again, this is a little bit more suited to high volume production. We don't have our electrode of set length, and we don't have this mess being made by the flux. Instead, we have our continuous wire feed, and here you'll see on the machine that I'm adjusting the voltage instead of the amperage. It's still very dependent on the thickness of the material to select the right one. Now, even though the arc light will still be very bright, it'll be difficult for you to see the arc itself. What I want you to do is listen very carefully to the difference in sound that this process makes. So definitely a distinctly different sound, as well as a distinctly different appearance of the weld itself. That's a very clean weld. There's no flux to hammer off. Very good weld penetration. This can go on to paint without having to be cleaned the way the shielded metal welds do. Okay, I thought I'd go through here with our final products and just take a look at them. First of all, I wanted to look at our sample plate with our 4 different fluxes and just give you a little bit better picture of what it looks like. Again, the 6011 up here, a very aggressive rod, lots of spatter, a relatively low deep penetrating weld pool, and then all the way down here to the 7000 series where you start to see very aesthetically pleasing welds, all dependent on the flux. So the flux coating of those shielded metal electrodes is extremely important. But let's look at our 4 samples that were welded at 4 different amperages. Over here at 50 amps, sample A broke, and there is really, see if I can get that to focus, there's really very little weld penetration that occurs. You can see the weld bead up here, but the weld bead is relatively thin and didn't offer much strength. The biggest problem though was almost no weld penetration. That 50 amps just wasn't quite enough to get through the material. Here, when we look at sample B, we can see that when the sample bent to break, they break, you bend them like so, it actually pulled some of the base metal up, so there was some deformation. It tried to pull the weld all the way over, but it still broke, and again, it broke because there just wasn't enough weld penetration inside. A little bit more weld cross-section, the added amperage gave the electrode a little bit more energy to transfer some material down onto the workpiece, but still a failure. Sample C, also some deformation all the way across, and here we can see some definite penetration, especially towards the end of the weld as it gets into the workpiece. You know, the workpiece had heated up as we were welding along. This one bent quite a bit before it broke. But lastly, sample D, remember I burned through a little bit through here, but sample D with complete weld penetration didn't fail at all. It managed to go past 90 degrees without breaking. So all of these welds, when they were flat, looked relatively similar. So that's why sometimes visual inspection of welds is not really sufficient. You have to have an experienced welder that can set the machine appropriately. So that is the results of this exercise.